A massive dark opening has torn across the face of the sun. Right now, as you sit here, something is streaming out of it at incredible speed, racing through space toward our planet. This process has been ongoing since mid-February 2026. Stay with me for the next several minutes. We're going to walk through exactly what this opening on the sun really is, why scientists are watching it so closely right now, what's flowing toward Earth at this very moment, and most importantly, what you might actually witness in your own sky over the coming nights. We'll also explore why this matters for the technology you use every day, and what's likely to unfold as the sun continues to turn. This dark region appeared just days ago. Space weather forecasters spotted it emerging on the sun's surface. A distinctive curved shape stretching across vast distances. It's not a sunspot, though we've been tracking plenty of those recently. It's not an explosion, though the sun has produced several powerful eruptions in recent weeks. This is something entirely different, something that creates a direct pathway from deep within the sun's atmosphere straight out into the solar system, and currently, this coronal hole is facing toward Earth. Scientists have a name for this phenomenon. They call it a coronal hole. When one of these structures opens up and faces Earth, what follows can illuminate our skies in ways that most people never experience in their entire lives. But the effects go beyond beautiful lights. They reach into the space around our planet, affecting Earth's magnetic field, which helps protect our planet from solar wind particles. This coronal hole is notable because of its size and location. This isn't a small feature tucked away near one of the sun's poles where its effects would miss Earth entirely. This is a large transequatorial coronal hole, one that bridges both the northern and southern regions of the sun in a single continuous structure. These are less common than other types, and they're known for producing especially strong and persistent streams of solar wind. Here's something you should understand right from the start. The solar wind isn't just a poetic name for empty space, it's an actual wind, a genuine flow of particles constantly rushing away from the sun in all directions. Under normal conditions, this wind moves at moderate speeds, taking several days to cross the enormous distance between the sun and Earth. But when a coronal hole opens, everything changes. The wind accelerates dramatically, sometimes reaching speeds nearly twice as fast as the background flow. That accelerated wind left the sun days ago. It travelled through the void of space, carrying with it the sun's magnetic field, moving in a stream that stretches for millions of miles, and now it's arriving. Instruments positioned between the sun and Earth have already detected the leading edge of this high-speed stream. Our planet's magnetic field is beginning to respond to the increased pressure. If you've been following space weather over recent weeks, you know the sun has been remarkably active. We've tracked multiple massive sunspot groups, some of the largest observed in years. These regions have erupted repeatedly, sending out powerful flares and massive clouds of solar material. Some of those eruptions triggered significant geomagnetic storms when they reached Earth, creating spectacular auroras visible much farther south than usual. What we're dealing with now is different. Those explosive events from sunspots are sudden and intense but relatively brief. They hit hard and then pass. A coronal hole operates on a different timescale. It doesn't explode, it simply opens and the solar wind pours through continuously, day after day, for as long as the hole remains facing Earth. Before we go further, I want to ask something of you. If you're curious about what's unfolding in the space between the sun and Earth right now, if you want to understand how these cosmic processes connect directly to the world around you, go ahead and hit that like button. It tells me this kind of content matters to you. And make sure you're subscribed to this channel, because we follow these developments as they happen, bringing you updates on space weather events that have real effects on our planet. Also, take a moment to drop a comment and tell me where you're watching from, because depending on your location, you might be in one of the regions where the effects of this solar wind stream could become visible in your night sky over the coming days. Now let's dig into what's actually taking place up there, because understanding this phenomenon requires us to think about the sun in a way that might be unfamiliar. The sun you see during the day, that bright disk crossing the sky from horizon to horizon, represents only part of what the sun actually is. The glowing surface you observe is just one layer of a much more complex structure. Beyond that visible surface lies an extended atmosphere, layers of superheated gas that reach far out into space, much hotter than the surface itself. The outermost layer of this atmosphere is called the corona. You've probably seen pictures of it, that beautiful pearly halo visible during total solar eclipses when the moon blocks the sun's bright disk. That halo isn't just a visual effect, it's a real physical structure. a region where temperatures reach over 1 million degrees, much hotter than the Sun's visible surface. Under normal circumstances, the corona is held close to the Sun by powerful magnetic fields. These fields emerge from below the Sun's surface, loop through the atmosphere and trap solar material in complex structures. The solar wind, that constant outflow of particles from the Sun, exists even under these normal conditions, but the closed magnetic field lines keep most of it contained, forcing it to escape slowly. But the Sun's magnetic field isn't static. It changes, it evolves, regions shift and reconfigure, and sometimes, in certain locations, the magnetic field doesn't close in loops. Instead, it opens. The field lines stretch straight out into space rather than curving back to the solar surface. When that happens, you get a coronal hole. From Earth, when we look at the Sun using instruments that can see in ultraviolet and X-ray wavelengths, these holes appear as dark regions. Not dark because they're cold. Here's what's happening. Dark because the atmosphere there is less dense, more tenuous. The material that would normally be trapped by closed magnetic fields is absent because it's streaming away into space, and that's the crucial point. A coronal hole isn't just an interesting feature to observe, it's an active structure that changes the way solar wind escapes from the Sun. The wind flowing through these openings moves faster, carries more energy, and creates a high-speed stream that extends through the solar system. Think of it as the difference between water seeping slowly through a barrier versus water rushing through an open gate. The amount of flow increases dramatically when the path is clear. That's what's happening right now. The magnetic field on a large section of the Sun's surface has opened up, creating a clear path for solar wind to escape at high velocity. And because of the Sun's rotation, because of where this hole appeared and when, that high-speed stream is currently flowing directly toward Earth. You might wonder how scientists know this. How can they track something invisible flowing through empty space? The answer involves a network of spacecraft positioned throughout the inner solar system. Some orbit Earth, constantly monitoring the space environment around our planet. Others sit at a special point between Earth and the Sun, about 1 million miles away, where the gravitational pull of both bodies creates a stable location. From there, these spacecraft act as an early warning system, detecting changes in the solar wind before those changes reach Earth. Over the past several days, as this coronal hole rotated into position facing our planet, forecasters watched and waited. They knew from the hole's size and characteristics that a high-speed stream would follow. The question wasn't if it would arrive, but when, and how strong it would be. The instruments upstream from Earth provided the answer. The stream began arriving over the weekend. Sensors registered a sharp increase in solar wind speed. Particles that had been moving at moderate velocities suddenly accelerated to much higher speeds. The density changed. The magnetic field carried by the wind shifted in strength and orientation. All of this data flowed into forecasting models. Scientists at space weather prediction centers analyzed the numbers, compared them to past events, and issued forecasts. Not warnings of danger, but predictions of enhanced geomagnetic activity. By Sunday, Earth's magnetic field was responding. Earth's magnetic field, an invisible shield surrounding our planet, began to show signs of disturbance. Energy built up in its structure as the high-speed solar wind pressed against it, compressing it on the side facing the Sun, stretching it out on the opposite side, and then the energy released. Geomagnetic storm conditions developed. These were moderate conditions typical during solar active periods, but significant enough to push auroras southward from their usual high-latitude locations, giving people in northern regions of the United States and similar latitudes elsewhere a chance to see lights they might only witness a few times in their lives. Reports filtered in through the night and into Monday. Montana, North Dakota, Minnesota, northern Wisconsin, upper Michigan. People stepped outside into cold darkness, looked toward the northern horizon, and saw pale glows, sometimes tinged with green, sometimes pulsing and shifting, and sometimes stretching upward in rays that seemed to reach toward the stars. Not everyone saw them. Weather played a role, as it always does. Clouds blocked the view in many locations. Light pollution from cities washed out the fainter displays. Timing mattered too, because auroras fluctuate, brightening and fading over minutes and hours. But for those who witnessed them, the experience created a direct personal connection to what's happening on the Sun right now. And here's what's happening. The solar wind stream continued flowing through mid-February 2026. That coronal hole remains in position, still facing Earth, still channeling high-speed solar wind in our direction. which means the effects we saw over the weekend are likely to continue. Perhaps not at the same intensity every moment, but the overall pattern of enhanced geomagnetic activity is expected to persist for days. So if you're in one of those northern regions, if you have clear skies tonight or tomorrow night, you might still have an opportunity to see auroras that wouldn't normally be visible from your location. But even if you're too far south, even if the lights remain beyond your horizon, solar activity continues in the space around Earth. Because this raises additional questions. Why does this happen? What makes a coronal hole different from the explosive solar eruptions we've been tracking? And scientists are examining whether this coronal hole appeared in January as well. Let me take you back to where this began. Not just days ago when scientists first spotted the coronal hole, but to an earlier chapter in this same story. In the middle of January, about a month before the current event, space weather observers documented a large coronal hole rotating into view on the Sun's face. Its characteristics stood out immediately. The shape was distinctive, a long curved structure stretching across the solar equator, connecting the Sun's northern and southern hemispheres. The technical term for this configuration is transequatorial coronal hole, and they don't appear as frequently as smaller, more isolated holes near the poles. When that January coronal hole faced Earth, the fast solar wind streaming from it triggered enhanced geomagnetic activity. For several nights, auroras appeared at latitudes lower than usual. People across northern states witnessed displays they hadn't seen in months. The event lasted for days as the high-speed stream continued to flow, gradually weakening only as the Sun's rotation carried the hole away from Earth-facing position. Then the Sun turned. Day by day, that coronal hole moved around to the far side, out of view from Earth, its effects no longer reaching our planet. The Sun rotates, but not the way Earth does. Earth is a solid body, rotating as a single unit. The Sun is made of gas and different parts rotate at different speeds. The equator spins faster than the poles. But on average, a feature on the Sun's surface takes roughly 4 weeks to complete one full rotation and return to the same position relative to Earth. 4 weeks from mid-January brings us to mid-February, and right on schedule, a coronal hole with remarkably similar characteristics appeared in Earth-facing position. Now, here's where scientific precision matters. Scientists are observing whether this is the same coronal hole from January or a new formation in a similar location. Or is it a new structure that formed in approximately the same location with similar properties? The truth is, distinguishing between these possibilities isn't always straightforward. Coronal holes aren't permanent fixtures with rigid boundaries. They're regions where the Sun's magnetic field has a particular configuration. That configuration can remain stable for extended periods, or it can evolve and change. A hole can close completely and then reopen in nearly the same place days or weeks later. What scientists can confirm is this. The coronal hole currently facing Earth shares many characteristics with the one observed in January. The shape is similar, the location matches. The size is comparable. Whether it's the same persistent structure or a reformation in the same region, the practical result is identical. A large opening in the Sun's magnetic field, positioned to send high-speed solar wind streaming toward Earth. And the pattern of effects we're seeing now closely mirrors what happened during that January event. The high-speed stream began arriving over the weekend. Space weather monitoring stations detected the characteristic signatures, increased velocity, shifts in the magnetic field orientation carried by the solar wind, changes in particle density. All of it pointed to the arrival of wind flowing through a coronal hole rather than material ejected by an explosive eruption. By Sunday, geomagnetic conditions had escalated to what forecasters classify as moderate storm levels. The official designation, G2 on a scale that runs from G1 to G5, indicates significant but not severe disturbance of Earth's magnetic field. At this level, auroras extend to lower latitudes than during quiet conditions, sometimes reaching northern tier states in the US and equivalent latitudes elsewhere. Let me be clear about what this designation means and doesn't mean. It doesn't indicate any danger to people on Earth's surface. You won't feel a geomagnetic storm, your body won't respond to it. Daily life continues without interruption for the overwhelming majority of people. The effects occur in space, in the region surrounding Earth where satellites orbit and where Earth's magnetic field interacts with the solar wind. Even there, the impacts during a moderate storm are manageable. Satellite operators monitor conditions and can take protective measures if needed. Some spacecraft may experience increased drag as Earth's upper atmosphere expands slightly in response to energy input from the geomagnetic disturbance. GPS accuracy might degrade by small amounts. Radio communications that rely on bouncing signals off the upper atmosphere can become less reliable. But these are technical concerns affecting specialized systems, not everyday disruptions for most people. The visible consequence, the one that captures public attention, is the auroras. When geomagnetic activity increases, when energy builds up in Earth's magnetosphere and then releases, that energy flows along magnetic field lines toward the polar regions. Now, charged particles that were trapped in space suddenly gain energy and cascade down into the upper atmosphere. There, roughly 60 to 200 miles above the surface, these energized particles collide with atmospheric gases. Oxygen and nitrogen molecules absorb the energy, become excited, and then release that energy as light. The color depends on altitude and which gas is involved. Oxygen at higher altitudes produces red auroras. Oxygen lower down creates the familiar green that dominates most displays. Nitrogen can add blues and purples to the mix. The result is what people standing on the ground see when they look northward on a dark night during geomagnetic disturbances. Glows on the horizon, arcs stretching across the sky, sometimes curtains of light that seem to ripple and flow, occasionally rays that shoot upward, creating the impression of searchlights pointed at the stars. Over this past weekend, people across a broad swath of northern states witnessed these displays. Social media filled with photos and reports. Someone in Montana captured green curtains undulating above a dark landscape. A viewer in Minnesota saw faint glows that brightened into distinct arcs before fading again. Reports came in from Wisconsin, Michigan, even a few locations farther south where observers with exceptionally dark skies caught glimpses. Not everyone who looked saw them. Clouds interfered in many areas. Light pollution from towns and cities drowned out the fainter displays. Timing played a role because auroral activity fluctuates, intense one hour, nearly absent the next, then surging again. But the activity was real and widespread. And here's the crucial point that separates this event from the explosive solar eruptions we've been tracking recently. Those eruptions, the ones triggered by massive sunspot groups, send out discrete bursts of material. A coronal mass ejection races through space, arrives at Earth, creates a sudden impact, and then passes. The geomagnetic storm it triggers typically peaks within hours and then gradually subsides over a day or two. A coronal hole operates differently. It creates a stream, not a burst. As long as that hole remains facing Earth, the high-speed solar wind keeps flowing. The stream may vary in intensity, stronger at some times, weaker at others, but it doesn't stop abruptly. It continues day after day. That's why the effects we saw over the weekend haven't ended. The stream is still arriving, or Earth's magnetosphere is still responding. Geomagnetic conditions remain elevated, not necessarily at storm levels every moment, but enhanced compared to quiet background conditions. Space weather forecasters expect this pattern to continue through the middle of this week at minimum. Some predictions extend the elevated activity even longer, depending on how the stream evolves and how persistently the coronal hole maintains its current configuration. For anyone hoping to see auroras, this extended timeline matters. You don't have just one night to try, you have multiple opportunities. Tonight, tomorrow night. Perhaps several nights beyond that. The key factors remain the same. You need to be at a latitude where auroras can appear during moderate geomagnetic activity. Northern states in the US, southern Canada, northern Europe, similar latitudes in Asia all have reasonable chances. You need clear skies because clouds block everything. You need darkness, real darkness, not twilight or dawn. And you need patience because auroras don't perform on command. They brighten and fade, appear and vanish, following patterns driven by processes in Earth's magnetosphere that fluctuate on timescales of minutes to hours. But the underlying cause, that high-speed solar wind stream flowing from the coronal hole, remains active. Particles that left the Sun several days ago reached Earth's magnetic field during February 14-17, 2026. The journey they made covers a distance so vast it's difficult to comprehend. They travelled through space that, while not completely empty, is far more vacant than any vacuum we can create on Earth. They moved at speeds exceeding 400 miles per second. And now they're here, interacting with the invisible magnetic shield that protects our planet, creating effects we can measure with instruments and, if conditions align, observe with our own eyes. This stream won't last forever. The Sun continues to rotate. Each day, the coronal hole shifts slightly as the solar surface turns. The angle changes. The stream that's currently aimed at Earth will gradually sweep past as the hole rotates away from Earth-facing position. By late this week or early next week, the geometry will have changed enough that Earth will no longer sit directly in the stream's path. When that happens, geomagnetic conditions will settle. The elevated activity will subside. Auroras will retreat to their normal high-latitude locations. But that won't be the end of the story. Because of a pattern we've already seen once and may well see again. The sun keeps turning. Features that rotate out of view eventually rotate back, assuming they persist long enough. And large coronal holes, particularly the transequatorial variety, often remain stable for multiple rotations, which raises an intriguing possibility. If this coronal hole maintains its structure, if the magnetic field configuration that creates it doesn't collapse or significantly evolve, then roughly 4 weeks from now, it will face Earth again. We've already seen this pattern once. The similar, possibly identical, coronal hole that appeared in mid-January produced its effects, rotated out of view as the sun turned, and now has returned a solar rotation later with characteristics that closely match the earlier appearance. If the coronal hole persists, it may face Earth again in late March. Of course, nothing about solar physics is guaranteed. The sun's magnetic field is dynamic, constantly changing in response to processes occurring deep in the solar interior. Coronal holes can persist for months, but they can also close or evolve over shorter timescales. A hole that looks stable for several rotations might suddenly shrink or merge with another structure. Forecasters will be watching as the sun continues to turn. If this coronal hole, or a similar structure in the same location, rotates back into Earth-facing position next month, we'll have advance notice. The hole will be visible on the far side of the sun before it rotates into view from Earth, giving scientists time to assess its characteristics and predict the likely strength of the solar wind stream it will produce. But even if this specific structure doesn't return, we're in a phase of the solar cycle where coronal holes are common. The sun is currently near or at the maximum of its 11-year activity cycle. During solar maximum, the sun's magnetic field becomes more complex, more tangled, creating conditions favourable for large coronal holes to form and persist. So while we can't predict with certainty that this exact hole will face Earth again, scientists expect that other coronal holes will likely appear and, when positioned appropriately, will send high-speed streams our way. This is part of the broader context you need to understand. Solar activity isn't random. It follows patterns driven by the solar cycle. Every 11 years or so, the sun transitions from a period of relative quiet, called solar minimum, to a period of heightened activity, and called solar maximum, and then back again. We're currently in solar cycle 25 and all indicators suggest we're near the peak. Sunspot counts have been high, solar flares have been frequent and in some cases extremely powerful. Coronal mass ejections have occurred regularly, and large, long-lived coronal holes have become more common. All of this is typical of solar maximum. The sun's magnetic field, which underlies every form of solar activity, becomes more dynamic during this phase. More energy is available, more instabilities develop. The result is increased activity across the board. Over recent weeks, you've probably heard about the massive sunspot groups we've been tracking. Some of these regions have been among the largest observed in years, sprawling across the sun's surface, magnetically complex and highly active. They've produced numerous significant solar flares, including several at the highest intensity levels on the classification scale. When sunspots erupt, they can launch coronal mass ejections, enormous clouds of solar material that race through space. If one of these clouds is aimed at Earth, it can trigger significant geomagnetic storms when it arrives, sometimes more intense than the effects from a coronal hole stream. Those explosive events are dramatic. They capture headlines, they create sudden impacts, but coronal holes play an equally important role in the overall space weather picture, just in a different way. Imagine two different types of weather systems on Earth. One is a powerful thunderstorm that rolls through quickly, dumping heavy rain, producing lightning and strong winds, and then moving on. The storm is intense but brief. The other is a steady atmospheric river, a prolonged flow of moisture that doesn't produce dramatic individual events, but delivers continuous precipitation over days. Both have significant impacts. Both require attention. But the character of those impacts differs. Solar eruptions from sunspots are like the thunderstorm. Sudden, intense, attention-grabbing. Coronal hole streams are like the atmospheric river. Steady, persistent, less dramatic in any single moment but potentially significant over time. We need to understand both. Right now, we're experiencing the effects of a coronal hole stream, but those massive sunspot groups are still on the sun's visible face. Some remain magnetically complex and capable of producing additional eruptions. As the sun rotates, these regions move across the solar disk. When positioned near the center of the disk as viewed from Earth, any eruption they produce has a high probability of sending material directly toward our planet. As the coronal hole rotates away from Earth, sunspot activity may still produce solar events. Space weather can change quickly. A quiet morning can turn active by afternoon if a large eruption occurs in the right location. This layering of different phenomena, coronal holes and sunspots both contributing to space weather, all driven by the same underlying solar magnetic field, is part of what makes this period near solar maximum so interesting from a scientific perspective. Researchers study how these different features interact. Does activity in one region influence what happens in another? How do global patterns in the sun's magnetic field affect the formation and persistence of coronal holes? What determines whether a sunspot region will produce a major eruption or remain relatively quiet? These questions drive ongoing research. Scientists observe, measure, model, and work to improve their understanding of the processes at work. And that improved understanding translates into better forecasts, more accurate predictions of when solar activity will affect Earth, and more time for operators of vulnerable systems to prepare. Because while geomagnetic storms from coronal holes or coronal mass ejections don't pose direct threats to people on the ground, they can affect space-based technology and occasionally influence ground-based systems. Satellites experience increased radiation exposure during enhanced geomagnetic conditions. The radiation belts around Earth, areas where energetic particles are held by the magnetic field, become more active. Satellites orbiting through these regions face a harsher environment. Electronics can be affected. Solar panels may age faster. In rare severe cases, spacecraft may experience technical issues. Satellite operators monitor space weather closely for this reason. When significant activity is forecast, they can take protective measures, orient spacecraft to minimize exposure, power down sensitive instruments temporarily, avoid risky maneuvers during peak storm conditions. GPS and other satellite navigation systems can also be affected. The signals these systems transmit travel through Earth's ionosphere, a layer of the upper atmosphere where solar radiation creates free electrons and ions. During geomagnetic storms, the ionosphere becomes more disturbed, more variable. Signal propagation changes. Timing errors can creep into position calculations. For most consumer applications, these errors are minor. But for applications requiring high precision, such as surveying or aviation, the degradation can matter. Radio communications that rely on bouncing signals off the ionosphere face similar challenges. The upper atmosphere layer that reflects radio signals changes during geomagnetic activity. Signals that would normally propagate reliably can fade or become erratic. Airlines flying polar routes sometimes have to adjust their communication strategies during storms, and in rare cases, during very severe geomagnetic storms, electrical currents can be induced in long conductors on the ground, particularly high-voltage power transmission lines. These currents can affect transformers and other power grid equipment. Most modern power grids have protective systems, though very severe storms may still pose challenges. The geomagnetic activity we're experiencing right now from this coronal hole doesn't rise to levels that would trigger major concerns about power grids or widespread satellite disruptions. This is moderate activity, notable, but not severe. However, it serves as a reminder that we live in an era where technology reaches into space and where space weather can affect some technology systems. Understanding what's happening on the sun, tracking coronal holes and sunspot eruptions, forecasting when high-speed streams or coronal mass ejections will arrive, all of this matters for maintaining the systems we've come to depend on. And beyond the technology, beyond the practical concerns, there's another dimension to this story that deserves attention. The simple fact that we can observe these processes, that we can track features on the sun, and watch their effects ripple out across the solar system to touch our planet represents a remarkable achievement. So let's turn to the question that's probably on your mind if you've stayed with me this far. What happens next? What should you expect over the coming days? Start with the timeline. The coronal hole is still facing Earth right now. The high-speed solar wind stream it produces is still flowing. Earth's magnetosphere is still responding to that stream with enhanced geomagnetic activity. This situation will continue for at least the next several days, but the sun rotates, slowly, steadily. The coronal hole is turning away from Earth-facing position. Each day the angle changes slightly. The stream that's currently aimed at our planet will gradually sweep past as the sun's rotation carries the source region out of alignment. By late this week, possibly extending into early next week, the geometry will have shifted enough that Earth will move out of the mainstream. When that happens, the elevated geomagnetic activity will subside. Conditions will gradually return to quieter background levels. The period of enhanced activity from this coronal hole is expected to last through approximately February 20th, 2026. After that, unless something else occurs, conditions will calm. Now let's talk about auroras specifically, because I know that's what many of you are most interested in. If you live in Alaska, northern Canada, Scandinavia, or other far northern regions, your chances of seeing auroras during this period are excellent. These locations see auroral displays regularly, and during enhanced conditions like we're experiencing now, the lights can be frequent and vibrant. But what if you live farther south? What if you're in one of those borderline regions that don't normally see auroras but sometimes get lucky during geomagnetic storms? Your chances depend on several factors. Let's walk through them. First, geomagnetic activity levels need to be high enough to push the auroral oval, the region where auroras typically occur, southward from its usual location near the poles. During the moderate storm conditions we've seen, auroras can extend down to latitudes that include northern states in the US Montana, North Dakota, Minnesota, Wisconsin. Michigan all have reasonable chances. Similar latitudes in other parts of the world have comparable opportunities, but geomagnetic activity fluctuates. It's not constant. Even during an extended period of elevated conditions, the intensity rises and falls. Some hours might see strong activity. Other hours might be relatively quiet. This variability means that even if overall conditions are favourable, you might look up at one moment and see nothing, then check again an hour later and find auroras visible. Second, you need clear skies. This might seem obvious, but it's worth emphasising. Clouds block everything. You can have the most spectacular auroral display occurring overhead, and if clouds cover the sky, you won't see it. Check weather forecasts for your area. Look for nights with clear conditions or at least breaks in cloud cover. Third, you need darkness. Real darkness, not twilight. Auroras occur high in the atmosphere, but they're visible from the ground only when the sky's dark enough for the relatively faint glow to stand out. During the depths of winter, northern locations have long nights, which helps. But as we move later into February and into March, nights are shortening. The window of true darkness shrinks. This means the optimal viewing time becomes more limited. Light pollution matters too. If you live in or near a city, the glow from streetlights and buildings washes out fainter auroral displays. Even a modest amount of light pollution can prevent you from seeing anything except the brightest auroras. Your best bet, if possible, is to travel away from urban areas to a darker location. Even a short drive can make a significant difference. Fourth, you need to be looking at the right time. Auroral activity often peaks during the hours after local midnight and before dawn. This is when the geometry of Earth's magnetosphere relative to the Sun favours enhanced activity. It's not a hard rule, and auroras can occur at any time during the night, but statistically the late night and early morning hours tend to be most active. Fifth, you need patience. Auroras are not like fireworks that start at a scheduled time. They're dynamic, driven by processes in Earth's magnetosphere that fluctuate constantly. You might go outside, see nothing for half an hour and be ready to give up, only to have auroras suddenly appear. Or you might see a faint glow that slowly brightens into something more distinct. Or you might catch a brief burst of activity that fades after 10 minutes. If you're serious about trying to see auroras, plan to spend time outside. Let your eyes adjust to the darkness, which takes at least 15 to 20 minutes. Look toward the north, because in the northern hemisphere, auroras appear in the northern part of the sky. At higher latitudes, they can be directly overhead, but at lower latitudes, they're usually near the horizon. And manage your expectations about what you'll see. Photography can capture colours and details that human eyes struggle to perceive, especially in fainter displays. Long camera exposures gather light over several seconds, making auroras appear brighter and more colourful than they look in real time. What shows up as vivid green in a photo might appear to the naked eye as a pale greyish or greenish glow. But even a pale glow is real. You're seeing photons generated by particles from the sun colliding with atmospheric gases. That's extraordinary, even if it doesn't match the dramatic photos you've seen online. Now, assuming you're willing to make the effort, what's the forecast for the next several nights? Space weather prediction centers issue regular forecasts based on current solar wind conditions, and models of how those conditions will evolve. As of right now, forecasts indicate that enhanced geomagnetic activity will continue through the middle of this week. Some predictions extend elevated conditions even further, depending on how the solar wind stream evolves. What this means practically is that each night over the next several nights offers a potential opportunity. Tonight might be active, tomorrow night might be even more active, or conditions might fluctuate. Strong one night, weaker the next. The best approach is to stay informed. Several websites and apps provide real-time space weather information and aurora forecasts. These resources can tell you when geomagnetic activity is spiking, which helps you decide when to make the effort to go outside and look. Some forecasts provide a probability that auroras will be visible at different latitudes. If you're in a borderline location, these probabilities can help you gauge your chances. A forecast showing high probability for your latitude suggests it's worth staying up late or setting an alarm for the middle of the night. A forecast showing low probability means you're less likely to see anything, though surprises do happen. As the week progresses and the coronal hole rotates further from Earth-facing position, the solar wind stream will weaken. Earth will gradually move out of the main flow, geomagnetic activity will decline, auroral displays will become less frequent and retreat to higher latitudes. By the weekend, unless something new develops, conditions will likely have returned to near-normal levels. The window for seeing auroras from this particular coronal hole will have closed, but remember, the sun is active. Those large sunspot groups are still present. Any of them could produce an eruption. If a coronal mass ejection occurs facing Earth, additional geomagnetic activity may develop completely independent of the coronal hole. Space weather is dynamic. Forecasts are based on current conditions and models, but the sun doesn't always cooperate with predictions. Solar activity can change quickly. Forecasts may be updated if new eruptions occur. This is part of what makes following space weather engaging. There's always an element of uncertainty. You're watching a dynamic system, one where multiple processes interact in complex ways, and while our understanding has improved dramatically, surprises still happen. So stay alert over the coming days, check forecasts, watch for clear skies. If you're in a location where auroras might be visible, make the effort to look. You might see something memorable, and even if you don't, even if clouds interfere or conditions don't peak at the right time or you're just a bit too far south, know that the processes creating these effects are still unfolding. Solar wind from that coronal hole is still washing over Earth's magnetic field. The interaction is still happening, whether you can see the visible result or not. But auroras are only the most obvious effect of this solar wind stream. Other consequences, invisible to casual observers but real nonetheless, are occurring simultaneously. Let's explore what those are, because they help explain why space weather matters beyond creating pretty lights in the sky. Here's a perspective shift that might change how you think about your place in the universe. You are, right now, living inside the sun's atmosphere. Not the hot, dense part that would vaporize anything instantly. Not the visible surface that glows brilliantly enough to hurt your eyes if you look directly at it. But the extended outer atmosphere, the corona, the region where temperatures soar to millions of degrees yet the gas is so tenuous it's essentially a vacuum by Earth standards. That atmosphere doesn't end at some sharp boundary near the sun. It extends outward, filling the solar system. The solar wind carries the sun's magnetic field with it, creating a vast structure called the heliosphere that reaches far beyond the orbits of the planets. Earth orbits within this heliosphere. Earth orbits within the sun's heliosphere. For most of human history, this connection went unrecognized. Our ancestors understood the sun as a source of light and warmth, essential for life but fundamentally separate from Earth. They had no concept of the solar wind, no knowledge of magnetic fields, no understanding that processes on the sun could affect our planet in ways beyond the obvious. That ignorance didn't matter much for most of history. Life continued regardless of what the sun was doing. Crops grew or failed based on weather and soil and water, not on geomagnetic storms. Human conflicts and achievements unfolded without any consideration of space weather. But something changed over the past century and a half. We developed technology. First came telegraph systems. Long wires stretched across continents carrying electrical signals. During a massive geomagnetic storm in the mid-1800s, telegraph operators reported strange effects, sparks flying from equipment, messages being transmitted even when batteries were disconnected. The auroras during that event were visible as far south as the Caribbean, an indication of how severe the disturbance was. Then came radio, power grids, satellites, GPS. all technology that either operates in space or depends on conditions in Earth's upper atmosphere, or uses long conductors that can be affected by currents induced during geomagnetic storms. Suddenly, space weather mattered in practical, concrete ways. Let me give you a specific example that illustrates the point clearly. In early spring of 1989, a powerful coronal mass ejection erupted from the Sun. The cloud of solar material raced toward Earth and arrived with tremendous force. The resulting geomagnetic storm was severe, among the most intense observed in decades. In Quebec, operators of the electrical power system watched as instrument readings became erratic. Currents induced in the ground by the rapidly changing magnetic field during the storm flowed into the power grid through grounding connections. These currents added to the loads the system was designed to handle. Protective devices tripped, transformers failed. Within seconds, the entire Quebec power grid collapsed. 6 million people lost electricity. Hospitals, businesses, homes all went dark. It happened in the middle of the night during winter when temperatures were well below freezing. Crews worked frantically to restore power. It took 9 hours to bring the system fully back online. During those 9 hours, the lack of electricity affected everything. Heating systems stopped. Traffic signals went dark. Water pressure dropped as pumps failed. The cause wasn't a storm on Earth. It wasn't an equipment failure. It wasn't human error. It was a storm on the Sun. That event served as a wake-up call for power grid operators worldwide. It demonstrated unambiguously that space weather could have real, significant consequences for critical infrastructure. Since then, utilities have improved their monitoring and protection systems. They work with space weather forecasting centers to receive advance warning of potential storms. When major events are predicted, they can take steps to reduce vulnerability. But the fundamental challenge remains. Modern technological civilization depends on systems that extend into space or that use long conductors that can act as antennas for geomagnetic disturbances. These systems are inherently vulnerable during severe space weather. Satellites face radiation exposure. The belts of trapped particles surrounding Earth intensify during geomagnetic storms. Spacecraft orbiting through these regions encounter more high-energy particles. Electronics can be damaged. Memory errors can occur. Solar panels degrade more quickly. In some cases, satellites have been lost entirely due to space weather effects. GPS accuracy degrades when the ionosphere, the layer of Earth's upper atmosphere where signals propagate, becomes disturbed. Position errors increase. Timing synchronization, which many systems rely on, becomes less precise. Radio communications using high-frequency bands can become unreliable. Airlines flying polar routes, where they can't rely on ground-based communication systems, sometimes have to reroute during storms to stay within range of alternative communication methods. None of this means that the moderate geomagnetic activity we're experiencing right now from this coronal hole poses a significant threat. The effects are manageable. Systems are designed with these conditions in mind. Operators know what to expect and how to respond. But it serves as a reminder of the connection between the Sun and Earth. It illustrates why we monitor space weather. It explains why forecasting these events matters. We live in a time when our technology reaches into the space environment, and that environment is not benign. It's dynamic. It changes in response to what the Sun does, and we need to understand those changes if we want to maintain the systems we depend on. Yet there's another dimension to this story, one that's easy to overlook amid discussions of technological vulnerabilities. The same solar activity that poses challenges also creates beauty. Those auroras dancing in northern skies right now are a direct consequence of the coronal hole stream. These solar wind particles flowing along Earth's magnetic field lines, accelerated to high energies, crashing into atmospheric molecules, releasing light. The process that worries satellite operators and grid engineers is the same process that creates one of nature's most spectacular displays. People who've witnessed vivid auroras often describe the experience as profound. There's something about watching light generated by cosmic processes unfolding overhead that creates a sense of connection to the larger universe. You're not just looking at a phenomenon, you're witnessing physics in action. Energy that began inside the Sun, released through a hole in the solar atmosphere, traveled across millions of miles of space, interacted with your planet's magnetic field, and ultimately produced visible light. All of that is happening because of where you are. A planet orbiting within the heliosphere protected by a magnetic field, graced with an atmosphere containing the right gases to glow when struck by solar wind particles. Other planets experience space weather too. Mars, lacking a strong magnetic field, has its upper atmosphere slowly stripped away by the solar wind over geological time. Jupiter, with a powerful magnetic field and a rapid rotation, creates auroras far more intense than anything Earth experiences. Saturn's auroras are visible in ultraviolet light. Even some moons show auroral effects. But Earth's auroras are special to us because we can stand on the surface and see them. We have dark skies, an atmosphere with nitrogen and oxygen, and a magnetic field that channels particles to the right locations. All the ingredients come together, and during periods of elevated solar activity like we're experiencing now, those auroras extend to latitudes where more people have the opportunity to witness them. That's worth something. It's worth stepping outside on a cold night. It's worth driving to a darker location. It's worth staying up past your usual bedtime, because in that moment, when you see auroral light in the sky, you're connecting with processes that span the solar system. You're seeing evidence of the Sun-Earth relationship. You're witnessing something your ancestors saw and wondered about, but you have the knowledge to understand what's actually happening. That knowledge doesn't diminish the wonder. If anything, it enhances it. Understanding the mechanisms makes the experience richer, not poorer. You appreciate not just that it's beautiful, but why it's beautiful. Not just that it's rare, but what makes it rare. Not just that it's happening, but how it's happening. And that's a gift that science provides. The ability to understand, to explain, to connect what you observe to the underlying physical processes. The capacity to look at light in the sky and trace it back to events on the sun, through the journey of solar wind particles, into the dynamics of Earth's magnetosphere, down to collisions with atmospheric molecules. All of it connects. All of it makes sense within the framework of what we've learned about how the universe works. And moments like this, when space weather creates visible effects, are opportunities to appreciate that understanding. Let me walk you through the actual mechanics of what's happening. Using plain language without the technical terminology that can make science feel inaccessible, start with the sun itself. It's not burning the way wood burns in a fire. The sun generates energy through nuclear fusion deep in its core, where temperatures and pressures are so extreme that hydrogen nuclei fuse together to form helium, releasing enormous amounts of energy in the process. That energy works its way outward through the sun's interior, eventually reaching the surface. What we see as sunlight comes from the sun's surface, the photosphere, where temperatures are around 10,000 degrees. But above the surface lies the atmosphere. The lowest layer, just above the photosphere, is called the chromosphere. It's visible during solar eclipses as a thin reddish layer. Above that is the corona, the outermost layer, visible as that beautiful pearly halo during total eclipses. Here's something that puzzled scientists for decades. The corona is much hotter than the layers below it. The surface is 10,000 degrees. The corona reaches temperatures of several million degrees. How does that work? How can a region farther from the sun's core, farther from the energy source, be hotter than regions closer in? The answer involves magnetic fields. The sun's interior is filled with moving, electrically charged plasma. These motions generate powerful magnetic fields. Those fields emerge from the sun's interior, pass through the surface, and extend out into the corona and beyond. Magnetic fields carry energy. When they twist, reconnect, or release stored energy, they can heat the plasma around them to extremely high temperatures. This is why the corona is so hot, but magnetic fields also trap material. Where field lines form closed loops, plasma is confined, it can't escape. The corona in these regions is denser, brighter when viewed in the right wavelengths. A coronal hole forms where the magnetic field doesn't close in loops. Instead, the field lines stretch straight out into space. Plasma isn't trapped, it flows freely outward. This is the solar wind. Under normal conditions, solar wind escapes from the entire sun at a steady rate. The wind is always flowing, always carrying material away from the sun, but where coronal holes exist, the wind escapes more easily, accelerates to higher speeds, and creates a high-speed stream. Think of it like water flowing through a channel. Where the channel is narrow and restricted, flow is slower and more turbulent. Where the channel opens up, flow accelerates and becomes smoother. A coronal hole is an open channel for solar wind. Now that high-speed stream doesn't travel through completely empty space, but space is close to empty. The solar wind is tenuous enough that if you were floating in it, you wouldn't feel anything like wind on Earth. The density is far too low, but Earth doesn't experience the solar wind as individual particles. Earth has a magnetic field, and that changes everything. Deep inside Earth's core, the outer core is liquid iron. This liquid iron flows in complex patterns driven by Earth's rotation and heat escaping from the inner core. These flowing currents of electrically conductive material generate Earth's magnetic field. That field extends far beyond the planet's surface, often creating a protective bubble called the magnetosphere. On the side facing the Sun, the magnetosphere extends outward for several Earth radii. On the opposite side, it stretches out into a long tail that extends farther than the Moon's orbit. The solar wind doesn't pass through the magnetosphere as if it weren't there. The wind carries the Sun's magnetic field with it, and when two magnetic fields interact, complex things happen. On the sunward side, the solar wind compresses the magnetosphere. Think of it like air pressing against a balloon. The pressure from the wind pushes the magnetic field inward. At the same time, some solar wind material can enter the magnetosphere through processes that occur when the Sun's magnetic field and Earth's field have certain alignments. This material gets trapped, adding to the population of charged particles already circulating in the magnetosphere. When a high-speed stream from a coronal hole arrives, the pressure increases. The magnetosphere compresses further, more energy flows into the system. That energy has to go somewhere. Part of it goes into accelerating particles already trapped in the magnetosphere. These particles gain speed, gain energy, and some of them spiral along magnetic field lines toward Earth's poles. Why the poles? Because that's where Earth's magnetic field lines converge. If you could see Earth's magnetic field, it would look somewhat like the field around a bar magnet, with lines emerging from one pole and curving around to enter the other pole. Charged particles tend to follow these field lines. When they gain energy from processes in the magnetosphere, they spiral along the field lines that lead toward the polar regions. As these energized particles descend into Earth's upper atmosphere, they encounter air. At altitudes between about 60 and 200 miles, the atmosphere is thin but not absent. Molecules of nitrogen and oxygen are present. When a high-energy charged particle collides with an air molecule, the impact transfers energy to the molecule. Specifically, the energy kicks electrons in the molecule to higher energy states. The molecule becomes excited. But atoms and molecules don't stay excited indefinitely. The electrons fall back to their lower energy states, their ground states, and when they do, they release the energy they absorbed. They release it as light. The specific color of that light depends on which molecule is involved and which energy transition occurs. Oxygen produces both green and red auroral light, depending on altitude and energy. Nitrogen can produce blue and purple. The result is the range of colors visible in auroras. What you're seeing when you watch an aurora is literally the glow of air molecules releasing energy they absorbed from solar wind particles. It's similar in principle to a neon sign, where electrical current excites gas atoms that then emit colored light. The mechanism is the same, just on a vastly larger scale and with different gases. Now, here's why coronal holes produce different effects than explosive solar eruptions. When a sunspot erupts and launches a coronal mass ejection, it sends out a discrete cloud of material. That cloud expands as it travels. When it reaches Earth, it arrives as a relatively sudden impact. The magnetosphere responds rapidly. Geomagnetic activity spikes quickly, often reaching peak intensity within hours, then gradually declining. A coronal hole, by contrast, creates a stream that's more like a steady flow. The stream has a leading edge, where the fast wind begins, and a trailing edge, where it ends, but in between, the flow continues steadily. As long as Earth is immersed in that stream, the effects persist. The result is different patterns of geomagnetic activity. A coronal mass ejection often triggers a storm with a sharp onset and a relatively quick recovery. A coronal hole stream produces more gradual, sustained activity that can last for days. Both can create auroras. Both can affect satellites and other technology. But the character of the effects differs because the underlying driver differs. Understanding this distinction helps make sense of space weather forecasts. When forecasters predict enhanced activity due to a coronal hole, they're telling you to expect conditions that build gradually and persist. When they warn of a coronal mass ejection impact, they're indicating a sharper, more sudden event. Right now, we're in the coronal hole pattern, sustained elevated activity as long as the stream continues to flow. That's why the effects started over the weekend and are expected to continue through this week. It's not a brief spike. It's an extended period of enhanced conditions, and as you now understand, those conditions arise from a straightforward sequence. A coronal hole opened on the Sun. Solar wind accelerated through that opening. The wind carried the Sun's magnetic field. The wind reached Earth. Earth's magnetic field responded. energy flowed into the magnetosphere. Particles were accelerated toward the poles. Those particles collided with atmospheric gases. Light was emitted. Each step follows from the previous one. The entire sequence makes sense within our understanding of how magnetic fields, plasmas, and atmospheric gases behave. That's the power of scientific understanding, taking something that might seem mysterious, breaking it down into components, explaining each component, and showing how they fit together into a coherent whole. And that understanding allows us to make predictions, which brings us to the question of what comes next, not just in the next few days, but in the weeks and months ahead. The sun doesn't sit still, it rotates, bringing new regions into view while carrying others around to the far side. This rotation means that the coronal hole currently facing Earth will soon turn away, but it also means that features on the far side will eventually rotate into view. So let's look forward and think about what the next several weeks might bring. First, the immediate future. This coronal hole will continue facing Earth for another few days, maybe a bit longer, but the angle is already changing. Each day, the sun's rotation shifts the hole slightly. By late this week, the geometry will have changed enough that the main stream of high-speed solar wind will no longer be aimed directly at us. Earth will move out of the stream's path. When that happens, the elevated geomagnetic activity we've been experiencing will subside. The effects won't stop instantly. Conditions will gradually decline back toward baseline levels. Auroras will retreat to their usual high-latitude locations. The magnetosphere will settle into its normal configuration. For a time, perhaps a week or more, space weather will be relatively quiet, assuming no new activity develops. But then comes the question everyone wants answered. Will this coronal hole face Earth again? If the structure persists, if the magnetic field configuration creating it remains stable, then yes, roughly 4 weeks from now, it will rotate back into Earth-facing position. One complete solar rotation later, we could see the pattern repeat. Another high-speed stream, another period of enhanced geomagnetic activity, another opportunity for auroras at lower latitudes. We've already seen this cycle once. A similar, possibly identical coronal hole appeared in January, produced its effects, rotated out of view, and returned now in February. If the pattern continues, a third appearance in March is entirely possible. Of course, the sun doesn't always cooperate with predictions. Coronal holes can close, shrink, change shape. The magnetic field configuration might not remain stable. By the time the next rotation brings that region back into view, the hole might be gone or significantly altered. We won't know until it happens. Forecasters will watch as the sun continues to turn. Before the hole rotates back into Earth-facing position, it will be visible on the far side of the sun, observed by spacecraft that monitor the entire solar surface. If it's still there, if it's still large and still looks capable of producing a significant stream, forecasts will go out warning of likely enhanced conditions. But even if this specific hole doesn't return, we're in solar maximum. Large coronal holes are common during this phase of the solar cycle. Other holes will form, some will be positioned to affect Earth, some won't. The overall pattern of elevated space weather is likely to continue for months, possibly a year or more, as the sun remains near peak activity levels, and then there are the sunspots. Multiple large active regions remain on the visible solar disk right now. Some of these have already produced significant eruptions. Others remain magnetically complex, capable of flaring at any time. As the sun rotates, these regions move across the face of the sun. When positioned near the center of the disk as viewed from Earth, any eruption has a high probability of sending material our way. One of these regions in particular bears watching. And sunspot groups that have produced major flares in the past often remain active for extended periods. The magnetic energy doesn't dissipate overnight. Subsequent eruptions can occur days or even weeks after the initial activity. If another significant eruption occurs, if it launches a fast coronal mass ejection aimed at Earth, we could see geomagnetic storms that are more intense than what the coronal hole has produced. Those explosive events can trigger sudden, powerful disturbances. And here's where it gets interesting. Space weather effects can overlap. A coronal hole stream can be flowing when a coronal mass ejection arrives. The combined effects can be stronger than either would produce alone. Activity from multiple sources compounds. This is part of what makes space weather forecasting challenging. You're not tracking a single phenomenon. You're monitoring an entire star with multiple active regions, various types of structures, all evolving simultaneously. Predicting exactly what will happen requires tracking all of it. So what should you do with this information going forward? If you're interested in space weather, if you want to catch auroras, if you just like staying informed about what the sun is doing, establish some habits. Check space weather forecasts regularly. Several reliable sources provide free, up-to-date information. Websites run by government agencies, apps designed for aurora enthusiasts, social media accounts maintained by space weather experts. Find sources you trust and check them often. When forecasts indicate elevated activity and you have clear skies, make the effort to observe. You won't see auroras every time conditions are enhanced, but you'll never see them if you don't try. If you work in an industry affected by space weather, you likely already have access to specialized forecasting services tailored to your needs, but staying generally aware of solar activity helps provide context for more detailed technical forecasts. For everyone else, simply understanding this connection between the Sun and Earth enriches your perspective. You recognize that space weather is real, that it has effects, that the Sun is not just a static ball of light but an active, dynamic star. That understanding changes how you interpret news reports about solar storms. It gives you context when you hear about auroras being visible at unusual latitudes. It helps you appreciate the complexity of the environment our planet exists within. And over the coming months, as we remain near solar maximum, there will likely be more events worth paying attention to. More coronal holes, more sunspot eruptions, more geomagnetic storms, more opportunities to witness auroras or to learn about the effects of space weather on technology. This coronal hole is one chapter in a longer story, the story of Solar Cycle 25, the story of a period of elevated activity that began a few years ago and will continue for perhaps another year before the Sun gradually transitions back toward quieter conditions. We're in the middle of that story right now, the most interesting phase, when activity is highest, when the Sun is most dynamic. And we have the tools to watch it unfold. Spacecraft observing the Sun continuously, instruments monitoring the solar wind, sensors tracking Earth's magnetic field, forecasting models that process all this data and make predictions about what will happen next. Our ancestors had none of this. They saw auroras and wondered. They noticed unusual effects during storms but couldn't explain them. They had no way to predict when the next event would occur. We do, and that capability represents a remarkable achievement. So as this coronal hole rotates away and the effects from its stream subside, don't assume the story's over. Stay curious. Keep watching. The Sun will continue doing what it does, and we get to observe, learn, and occasionally witness the visible consequences. That's a privilege worth taking advantage of. Think about where you are at this moment. You're on the surface of a planet, a rocky world orbiting a star at a distance that allows liquid water to exist, that permits an atmosphere to persist, that makes life possible. But you're not isolated. You're not separate from the rest of the solar system, safe behind some impenetrable barrier. You're part of it, connected to it, immersed in it. Right now, particles from the Sun are arriving in the space around your planet. They left the Sun days ago, poured through an opening in the solar atmosphere, travelled across a distance so vast it's hard to comprehend, and reached Earth. Your planet's magnetic field is responding. Energy is flowing through the magnetosphere. Particles are being accelerated along invisible field lines. Some are descending into the upper atmosphere, colliding with air molecules, creating light. All of this is happening whether you're aware of it or not, whether you're paying attention or going about your daily routine without giving it a thought. But knowing it's happening, understanding the processes at work, changes something. It shifts your perspective, even if just slightly. You're not just living on a planet, you're living on a world that exists within the extended atmosphere of a star, a world that experiences space weather, a world where cosmic processes reach down and create effects you can observe. That's extraordinary. For most of human history, people looked at the sky and saw mystery. The Sun rose and set, stars appeared at night. Occasionally, strange lights danced across northern skies, inspiring wonder and stories but no real understanding. We live in a different time. We can explain what those lights are. We can track the events on the Sun that cause them. We can predict with reasonable accuracy when they might appear. That knowledge doesn't diminish the wonder, it enhances it. Because now when you see an aurora, you're not just watching something beautiful, you're witnessing the visible proof of connections that span the solar system. You're seeing evidence of magnetic fields, of particle acceleration, of energy transfer between the Sun and Earth. You're observing natural atmospheric processes created by solar activity. And even if you never personally witness an aurora, even if your location or circumstances don't permit it, Knowing that these processes are occurring connects you to the larger environment in which Earth exists. We orbit within the Sun's domain. We are constantly bathed in the solar wind. Our magnetic field is constantly interacting with that wind. Most of the time, the interaction is subtle, invisible, unremarkable. Background processes that continue regardless of whether anyone notices. But sometimes, during periods of elevated solar activity like we're experiencing now, the effects become strong enough to create visible consequences, strong enough to remind us that we're part of a dynamic system, not isolated observers. This coronal hole that opened on the Sun last week is one of those reminders. This is a natural solar process. It's simply nature operating according to the same physical laws that govern everything in the universe. The Sun's magnetic field opened up. Solar wind accelerated through that opening. The wind reached Earth. Earth's magnetic field responded. Energy was transferred. Particles were accelerated. Light was created. Each step follows from the previous one. The entire sequence makes sense within the framework of what we understand about how magnetic fields and plasmas behave, and we get to observe it, study it, learn from it. That's a gift. The ability to understand the universe we inhabit, the capacity to explain phenomena that would have seemed miraculous or mysterious to earlier generations. So if you have the opportunity over the next couple of nights, if you're in a location where auroras might be visible, if skies are clear and conditions favourable, step outside, look north, be patient. If you see those lights, take a moment to appreciate what you're seeing, not just colours in the sky, but a window into the physics connecting your planet to its star. A visible manifestation of processes that span millions of miles. A reminder of the dynamic environment you exist within. And if you don't see them, if clouds interfere or you're too far south or timing doesn't work out, know that the processes are still happening. The solar wind is still flowing. The magnetic field is still responding. The connection between Sun and Earth is real and active, whether or not it produces visible effects from your location. This video aimed to help you understand what's happening right now in the space around Earth. A coronal hole on the Sun, a high-speed stream of solar wind, enhanced geomagnetic activity, potential auroras, all of it connected, all of it part of the ongoing interaction between the Sun and our planet. If this deepened your understanding, if it gave you context for what you might see in the news or in the sky, hit that like button. It helps others discover this content. Subscribe to the channel if you want to stay informed as space weather continues to evolve. We track these events, providing context and explanation as they unfold. And drop a comment. Let me know where you're watching from. Tell me if you saw auroras from this event. Share your thoughts about the Sun-Earth connection and what it means to you. We're all under the same sky. We're all experiencing the same space weather, and there's value in understanding the forces that connect us to the star at the center of our solar system. The coronal hole is still there, the stream is still flowing, the effects continue, and somewhere tonight, under dark skies far enough north, auroras are painting light across the atmosphere. Maybe you'll be fortunate enough to witness them. Maybe this will be the event that gives you that opportunity. Either way, you now understand what's happening. You know what causes it. You recognize the connection between distant processes on the Sun and visible effects here on Earth. And that understanding is worth having regardless of whether you ever see the lights yourself.